Chemical activity is at the core of how matter interacts in our universe. In this video, we'll explore what makes atoms chemically active and the principles that govern their behavior. First, let's understand what we mean by chemical activity. Chemical activity refers to an atom's tendency to react with other atoms to form chemical bonds. This reactivity is fundamental to all chemical reactions that occur in nature and in laboratory settings. To understand chemical activity, we first need to examine the electronic structure of atoms. An atom consists of a nucleus containing protons and neutrons, surrounded by electrons that orbit in shells or energy levels. The way these electrons are arranged in shells is called the electron configuration, and it's the key to understanding chemical activity. One of the most important principles governing chemical activity is the octet rule. The octet rule states that atoms tend to gain, lose, or share electrons to achieve a full outer shell of 8 electrons, similar to the electron configuration of noble gases. Noble gases like neon and argon have complete outer shells, which makes them chemically stable and generally unreactive. Now, let's explore the 3 main ways atoms attain chemical activity by trying to achieve a full octet. 1. Losing electrons to form positive ions, cations. 2. Gaining electrons to form negative ions, anions. 3. Sharing electrons through covalent bonds. Let's take a closer look at the first method, losing electrons to form cations. Here's a sodium atom with 11 electrons, 2 in the first shell, 8 in the second shell, and 1 in the outermost third shell. When sodium loses its outermost electron, it achieves the stable configuration of neon with 8 electrons in its outer shell. This creates a sodium ion, Na+, with a positive charge. This makes sodium highly reactive, especially with elements that readily accept electrons. Now let's examine the second method, gaining electrons to form anions. Here's a chlorine atom with 17 electrons, 2 in the first shell, 8 in the second shell, and 7 in the outermost third shell. When chlorine gains 1 more electron, it completes its outer shell with 8 electrons, achieving the stable configuration of argon. This creates a chloride ion, Cl, with a negative charge. This makes chlorine highly reactive with elements that readily donate electrons, like sodium. The third method of attaining chemical activity is by sharing electrons through covalent bonding. Let's look at 2 hydrogen atoms. Each has only 1 electron, but needs 2 to achieve a full outer shell, like helium. When 2 hydrogen atoms come together, they can share their electrons, allowing each atom to feel like it has 2 electrons in its shell. This creates a hydrogen molecule, H2, with a covalent bond. Both atoms now have the electron configuration of helium, a noble gas. Now, let's see how the first 2 methods combine to form an ionic bond. When sodium and chlorine come together, sodium donates its extra electron to chlorine. This electron transfer creates a sodium cation, Na+, and a chloride anion, Cl. The opposite charges attract, forming an ionic bond. This is how table salt, or sodium chloride, NaCl, is formed. Let's look at another example of covalent bonding, water. Oxygen needs 2 more electrons to complete its outer shell, while each hydrogen atom needs 1 more electron. When they come together, oxygen shares electrons with 2 hydrogen atoms, forming 2 covalent bonds. This creates a water molecule, H2O. Each atom now has a filled outer shell. What determines whether atoms will form ionic or covalent bonds? The answer lies in electronegativity. Electronegativity is an atom's ability to attract electrons. When there's a large difference in electronegativity between atoms, they're likely to form ionic bonds through electron transfer. When atoms have similar electronegativity values, they tend to share electrons, forming covalent bonds. To summarize, atoms attain chemical activity by trying to achieve a full outer shell of electrons, similar to the noble gases. They do this by 1. Losing electrons to form positive ions. 2. Gaining electrons to form negative ions. 3. Sharing electrons to form covalent bonds. This drive for stability through chemical activity is what creates the incredible diversity of compounds in our world, from the salt on our table to the water we drink.